Okay, so this the talk that I'm going to give today is about this paper that I did together with my co-authors, Marco De Bruin and Jordi Villageral and Paulo Artacho. So this was part of my one project that I worked on that I now have proposals going on to advance. So this is the origin of several ideas that I have about the clouds over the Amazon. So I will just start this discussion here. So, okay. So first, I will just shortly introduce a little bit about the scientific importance of shallow cumulus in the Amazon. Then we are gonna go ahead to the paper results in where I try to quantify, because I saw some other papers in the literature talking about wind shear, that it affects clouds and how it can affect also deep clouds. But I never saw a paper that told me how much a cloud changes its morphology based on wind shear. So in this study, I was trying to quantify that to see how significant it is. And then later found out from this paper that there are potential secondary effects that wind shear causes on the cloud field as a whole. So I will just give more details as we go. So firstly, the cumulus clouds over the Amazon. Here is just a video showing a satellite image over the region. This is daily cycles over a 4-month period. And you can see that when the sun rises, the clouds starts to grow. And there are obviously a lot of deep clouds, but you can see in the background, you have a lot of smaller white dots, that those are the shallow clouds that I'm interested in this study. And my idea is that those clouds support the development, the formation and development of the deep clouds in the region as well. So we at least we can think that the shallow clouds are not that important for the climate because they are very shallow, so they reflect, and they are smaller, so they reflect less radiation and so forth. But as you can see here in this animation, they are what they lack in depth, they make up for in numbers. So they cover large areas and they are present basically almost every day in the Amazon. And they also contribute to redistributing the energy both vertically as well as horizontally. So I would say the shallow clouds, they are quite important for the Amazon climate as well as for the global climate. And we can see the same thing about shallow clouds in other regions, right, for different mechanisms. But just to highlight how important the shallow clouds can be. So one thing that the shallow clouds can contribute to deeper convection is through the preconditioning mechanism. So when you have the shallow clouds growing, at some point they are going to grow and then dissipate. And this occurs several times during the day. It's not only like one cloud, shallow clouds forming during the whole day, several shallow clouds forming and dissipating. And this releases moisture in the lower and mid troposphere that then allows the next generation of clouds to reach deeper heights. Because if another cloud is formed, and then it's going to reach a layer with more moisture, and then it will have more buoyancy, and then it will be able to grow into a deeper cloud. So for the Amazon, this has another consequence, because studies have shown that the deep clouds and the aerosol cycle in the Amazon are tightly linked together, because the forest emits the biogenic volatile organics that are then carried by cloud updrafts to the upper troposphere, where they reach the temperature and pressure conditions that the gases can condense into small particles. And those particles then start to grow into larger sizes, CCN sizes, and they are also carried downwards. At least this is one of the explanations. We are not completely certain of all the mechanisms that bring these types of particles downwards. But one reasonable explanation is that a deep cloud, another deep cloud, will have downdrafts that carry the particles downwards towards the boundary layer, that they continue to grow and then help form new clouds. So this is the natural cycle in the Amazon that was identified, and the recent campaign Café Brazil was aimed at further detail in explaining all the mechanisms involved. So soon, in the next few years, we will have some more details about it. And so what is the role of wind shear in shallow cumulus clouds? So I looked up into the literature and I found one of the first papers that studied the effects of wind shear came in the 50s. And there's like a direct effect of wind shear in the cloud. This is due to the cloud tilting. So if you have no wind shear, the cloud is going to grow mostly vertically. But if you have wind shear, then the cloud is growing, and then it grows to the sides, and then it's tilted. So what happens here? This is one figure from this paper in the 50s that shows the stronger winds in the cloud base and weaker winds at cloud top, right? It doesn't matter if the wind is getting faster or slower with altitude. All that matters is if it's changing, also changing direction as well. Then the cloud is tilted a little bit, and what it causes is that the air is moving upwards diagonally instead of vertically. Then naturally the vertical component of the wind is smaller just because of the geometry. And then this makes the cloud a little bit slower to grow in depth, and also makes it more susceptible to dilution effects. So dilution via entrainment will make the updrafts weaker as well. So overall, this is the most direct way in which wind shear affects the shallow cloud formation and growth. But if you think about a single cloud, but then if you think about cloud field, then the situation can be a little bit more complex. So this is a paper from 2019 from Yamaguchi, and they ran a LES model in a domain by 48 by 48 kilometers. And on the left here is the cloud field without wind shear. So you can see the clouds are very spread, and the colors, I don't know if you can see it, but the colors represent rainfall. So basically, there's a bit of rainfall spread throughout the clouds that were able to grow a little bit more. But then when you add wind shear, this is a 30-hour run, right? So not exactly one daily cycle in the Amazon, so it's more. This is for trade wind cumulus in the ocean, so it's a bit more reasonable to do 30-hour simulations. And they noticed that the clouds tend to get more clustered together. So if the entrainment dilution causes evaporation. So if you think about one cloud, then the cloud is more prone to evaporation, to dissipation because of wind shear. But if you think about a cloud field, then the situation changes a little bit because there are competing effects. One effect is the first one that I mentioned, and the second effect is that because this evaporation at the cloud edges, they will release moisture, and then the next generation of clouds will tend to form in that region because it's easier to form a cloud there than in other places that are drier. So this tends to group the clouds together like it shows here. And then if a cloud is larger, then it protects itself from dilution effects via entrainment. So you can see that there are another secondary effect that you add when you consider cloud fields instead of only single clouds. So this was something that I was interested in looking for the Amazon. Oh, and another effect is that they show a little bit more rainfall because of the larger cloud cluster that were able to form there. So those are the two effects that I mentioned. So opposing effects of vertical wind shear. And in one hand, weaker updrafts leading to a stronger dilution via entrainment. On the other hand, more clustering leading to weaker dilution. And what happens when you have the shallow clouds tied to the daily cycle? Are they subject to those effects as well? Or is it the daily cycle too short for those processes to take place? So that's one of the questions that I wanted to address here. So what I did some LES simulations as well. I used the Dales model from the Netherlands. And I used a domain of 21 by 21 kilometers horizontally and 5 kilometers vertically. The resolution is 50 meters horizontal and 20 meters vertical. Time steps are a maximum of 1 second. And I did 12-hour simulations from 6 a.m. to 6 p.m. local time to simulate the daily cycle. And I output information every 2 minutes. And I prescribed the surface fluxes. So those are very idealized simulations. So this model doesn't even include topography, those simulations, for instance. So it's just a flat surface with prescribed latent and sensible heat fluxes, simulating a daily cycle, normal daily cycle, increasing and then decreasing. And the Bowen ratio varies between 0.1 and 0.4, which is typical of tropical forests. And the model uses two-moment bulk microphysics. So those are the profiles of that I initialized the model with, moisture and temperature, moisture on the right, temperature on the left. And those were obtained from this paper from 2020 from Villa-Guerral de Arellano. And they were based on radio sounds launched during typical shallow cumulus days in the dry season. And then, so you can see that the temperature profile at 6 a.m. is rather stable. So it will not form like deep convection or so. And then we just add a little bit more moisture to the boundary layer to make sure that we can initialize clouds. And also so this is horizontally homogeneous throughout the domain, but on the surface we add random temperature perturbations to initialize clouds. And then what I did is that I did 6 simulations in total. So the first simulation is the reference, and I have here the vertical profiles of the wind components. And the dark blue continuous line is the reference one. I call it NS because it's no shear. So this run has constant winds throughout the whole domain, at least initially, right? So the clouds and then the model itself will change it afterwards, but this is the initial profiles as well as the large scale forcing. And then the continuous lines here, I add on the MS case, medium shear case, I add 1.2 meters per second every kilometer in height. So the wind is getting faster with height. And on the HS case, the yellow curves here, I add double that amount of wind shear, so high wind shear case. And on the same lines, for the same colors, the dashed lines, they have the same wind speed configuration, but I also add wind rotation of totaling 90 degrees between surface and the top of the domain at 5 kilometers. So the wind also changes direction. And this is just the first glance at the results. So this is the liquid water path fields for the domain. So here's on the vertical axis is just y direction, south north, and then on the horizontal axis is just west and east. And the colors, sorry, this is not liquid water path. This is cloud top height for that for every pixel. So the deeper clouds will look more yellowish, greenish, and yellowish, and the shallow clouds were more bluish. So on the left here is no wind shear case. On the right is the high shear case. What I wanted to highlight here is one. Let the look go again. But on the left, you will see that the clouds are slightly more spread, and on the right, they tend to cluster together a little bit more on the afternoon and 1 o'clock. You see it, but it's very much harder to see than the paper I showed earlier. But you'll see here on the bottom left of the high shear case, a deep cloud was developed, and then no deep cloud was developed on the no shear case. So this gave me the idea of the competing effects, that even though the wind shear can help dilute clouds, it can also help promote deeper clouds, but we will get more in details. So this is one example of snapshot at 3 p.m. local time. What I'm talking about here is you can see that there are fewer clouds on the high shear case with the deep cloud here on the bottom, and no deep cloud on the no shear case with a bit more clouds. But again, not as extreme a case as the 30-hour simulation I showed earlier. So what I do is I track every cloud that I can. And so I apply a tracking algorithm on the shapes, so cloud shapes. I use the liquid water path from between 800 meter and 1.5 kilometer heights. And I just do a 2D tracking to track the shapes. So on the right here is one example. So the colors is the liquid water path of one cloud, and the black square is the current time step that I can track the cloud, and the lighter colors are the previous time steps of that cloud. So it started here as a light gray, and then it evolved a little bit toward north, and then it grew a little bit, and then in this time step, this is how it looks. So I can follow the clouds, and then I can store the whole 3D block of data for each cloud that I track. So in this way, I can have like a Lagrangian sense of the clouds. And I will talk about more why I do this. And then, in terms of cloud size distribution, for all the cases here, all the figures, whenever you see dark blue is no wind shear, whenever you see yellow is high wind shear. So I will focus mostly on that distinction because the other cases are intermediate, right? So, I noticed that equivalent cloud diameter horizontally increased with wind shear. You can see here on the bottom is the probability density function ratio. So basically telling me that clouds above 1.2 kilometers horizontally with diameters more than 1.2 kilometers are about more than 50% frequent in simulations with high wind shear. And in terms of cloud depth, is the opposite. So on the top here is the probability density function for cloud depth, and on the bottom is the ratio between those curves. So it's the same thing. So basically, clouds that are shallower than 1 kilometer are more frequent in the high shear case than the no shear case. That's basically the message here. And this is both to cloud tilting and dilution. So if the cloud is tilted, it will be shallower by geometry, but as well as by dilution, having weaker updrafts. So this is where the Lagrangian view of the clouds come in. So this figure is quite a lot of information, but I'll try to break it down. So on the y-axis is the relative depth of each cloud. So 0 is cloud base, 1 is cloud top. And then on the x-axis, on the horizontal axis, is equivalent diameter. So I take the area of the cloud in that altitude, height, and then I convert this area to one equivalent diameter of a circle having the same area. So just to have an idea, because clouds are not perfect circles, just to have an idea of the size of the clouds. And I do that for the early life cycle of the clouds in blue, mid life cycle in green, and late life cycle in yellow. So this is relative time in colors. 0 is the first time the cloud was detected by the tracking algorithm, and yellow is at the end of the life cycle. So what I see here, and I also separate this calculation for the all cloud. Only for the cloud cores, I define a cloud core based on updraft, buoyancy, and supersaturation, and only for the cloud margins. I wanted to see if the cloud margins would grow and the cores would decrease or something like this, but I didn't find it. What I found was that wind shear increases the horizontal dimensions of the clouds, both on the cores as well as on the margin. So the clouds are just larger horizontally as a whole, and this happens mostly in the middle of the cloud and less so on the cloud base and cloud top, right? This is to be expected. And so, but the average effect is very small. So remember that I use horizontal resolution of 50 meters, and I found average differences of about 50 meters. So let's say on the cloud core here, it goes about 340 to the core is even less than 50 meters on average. So it's hard to say from that 50-meter resolution if this is just an effect of the resolution, but you can see the message here is that the wind shear changes very slightly the cloud field, the cloud morphology. And the cloud, I was able to confirm that the core volume fraction and core mass fraction was reduced throughout the whole cloud life cycle. So those figures are the volume fraction and the mass fraction as function of relative time of every cloud, average for the clouds sharing the same duration. So clouds that have only 2-minute duration, they are on the blue colors here, and clouds that have 18-minute duration, they are on yellow curves. And the high shear cases are the dashed dotted lines, and the continuous lines are no shear case. So you can see that the fractions tend to be lower when you have wind shear. So the dilution effect is indeed taking place here. And the effects are a bit more apparent, not at the beginning of the life cycle of the clouds, but later on, which I guess it takes a little bit of time for the wind shear effect to take place. So in terms of the pure quantifications of the wind shear effects on the cloud geometry and morphology, we learned that the clouds subject to wind shear are shallower and have higher horizontal dimensions. But we did see in the early snapshot that we have like a big cloud forming in the high shear case. So why does wind shear decrease the average depth of clouds, but then you can enable a deeper cloud? And I should say that this deeper cloud is the only one that is precipitating significantly in these runs. And what is the mechanisms for that? So what I mentioned before, I noticed that for the clouds that are growing under heavy wind shear, they are growing slower and they have more area. So they release more moisture to the atmosphere as compared to the non-shear case. So on the left here, you can see the high shear case is the yellow curve, and the no shear case is the blue curve. And this is this profile is accumulated liquid water content that was released to the atmosphere between 11 a.m. and 2 p.m. So just before the big cloud formed in the high shear case. And you can see that you have significantly more moisture being released when you have higher shear. And this would lead, in about 0.2, 0.3 grams per cubic meters at about 2 kilometer height. So when the clouds, the new generation of clouds reach, the cloud base is about 1 kilometer here, and then when they reach 1 kilometer depth, then they will reach an atmosphere layer with more moisture so that they can keep growing. And this is, I was trying to quantify the clustering effect. And then what I calculated was the number of clouds in each time step divided by the average liquid water path of that cloud field. So what this tells me, for the same amount of water overall in the domain, how many clouds are there. So you can see here that you have more clouds for the same amount of cloud water in the non-shear case than you have for the high shear case. And there is an increase of about like 50% or so between 11 a.m. and noon. But then it starts to get closer together. But at least for the shallower clouds, we could see the effect of clustering. And so that's my study for today, my presentation. So the summary is that vertical wind shear in the Amazon, where you have a daily cycle, so the clouds have a limited time to suffer the effects of wind shear. So vertical wind shear leads to a small increase in horizontal cloud core and margin dimensions. What I attribute to the clouds having less time to grow on the daily cycle than in maritime clouds, for instance. And vertical wind shear leads to the decrease in updraft strength as well as cloud depth, and also decreases the core mass and volume fractions. But such weaker clouds with larger horizontal dimensions lead to increase in evaporation that leads to the more clustering and maybe what I call here spatial optimization of the preconditioning effect. So if the clouds are more clustered together, they will release moisture in a specific region in the domain, and then it will precondition that region, not the whole domain. So that's what I mean by spatial optimization. And that's what I have for today. So thank you.